I'd like to look at two special cases that may come up when you're solving a system of equations. So let's take a look first at this system of equations here. What we're going to do is I'm going to go ahead and I'm going to solve this system, and I'm going to use elimination to solve it. So I'm going to first eliminate x. I'm going to use this x up here, and I'm going to eliminate these two x's in the second two equations. I'll name this one A, this one B, and this one C. So the first thing I'm going to do is negative 3 times equation A plus equation B. Let's see. So equation A will stay the same. Negative 5y plus 5z equals negative 3. And when I multiply negative 3 by x, I get negative 3x plus 3x is 0. When I multiply negative 3 by negative 5y, I get 15y, and minus 2y would be 13y. When I multiply negative 3 times 5z, I get negative 15z, plus z would be negative 14z. Negative 14z. And lastly, when I multiply negative 3 by negative 3, I get 9, and 9 plus 5 is 14. So that is the result of multiplying equation A by negative 3 and adding it to equation B. Equation C stays the same also, plus 7z is equal to negative 14. So I still have this top row, which I'm calling equation A, the middle row I'm calling equation B, and the bottom row C. All right, now I'm going to go ahead and I'm going to eliminate x from the third equation by multiplying the top equation by negative 7. So I'll have negative 7 times equation A plus equation C now. All right, let's see what that yields. Well, equations A and B are going to stay the same, so I'll have x minus 5y plus 5z, z equaling negative 3. I'll have 13y minus 14z equaling 14. And I'm going to take equation A, multiply it by negative 7, and add it to equation C, and replace equation C with that result. So negative 7 times 1x is negative 7x, plus 7x is 0. Negative 7 times negative 5y is going to be 35y. And when I add 35y to um, negative 9y, I get 26y. And then negative 7 times 5z is negative 35z. When I take negative 35z and I add to it 7z, I get negative 28z. And this is equal to, when I multiply negative 7 by negative 3, I get positive 21. And when I add 21 and negative 14, I get positive 7. So that's the result of multiplying equation A by negative 7 and adding to equation C. This is still A, the first row. This is still B, the second row. And this is still C, the third row. So now I've eliminated the x's from two of the equations. So that means I have two equations now that only have two unknown values, b and c namely. So I'm going to try to eliminate one of those unknown values from uh, either b or c. So I'm going to multiply the top equation, or the middle equation, b, by negative 2 and add it to equation c. So equation A will stay the same. Equation A is still x minus 5y plus 5z is equal to negative 3. Equation B is going to stay the same. 13y minus 14z is equal to 14. The one that's going to change now is equation C. I'm multiplying equation B by negative 2 and adding it to C. So negative 2 times 13y is going to be negative 26y. plus 26y would be 0. All right. Negative 2 times negative 14z is positive 28z, plus negative 28z gives me a 0 for the left-hand side. So the left-hand side of this bottom row, row C, the left-hand side becomes 0. Let's see what the right-hand side is. Let's see. Negative 14 times, or sorry, 14 times negative 2 is actually negative 28, and negative 28 plus 7 is negative 21. Negative 21. So take a look at that bottom row. Here's where we have the special case. All the variables are gone from this equation. If you ever have a case where all the variables disappear from one of your equations or from an equation that you're solving, it means that you have one of the special cases. This special case, because this equation that we get with no variables is a false statement, right? It's a false statement to say that 0 is equal to 21. 0 is indeed not equal to 21. So whenever you get a false statement, you can say that there is no solution. There is no solution. And you can actually say that this is an inconsistent system. So we've identified that this system is inconsistent, and being inconsistent, there is no solution. There is no point where all three of these lines cross each other. So that's one special case, the case where there's no solution. Let's take a look at this second special case here. All right, so I have a second system of equations here. And what I'm going to do is I'm going to go ahead and I'm going to solve this system. And to solve this system, I'm actually going to use substitution rather than elimination like I used on the last one. So what I'm going to do first here is I'm going to solve this top equation for x. Solving this for x gives me x is equal to, and I'll have 1, and I subtract 3y from both sides, so I'll have minus 3y, and I'll also add 9z to both sides, so I'll have plus 9z. Excuse me there. 9z. All right. So moving along, what I'm going to do now is I'm going to substitute that value for x in my other two equations. So the other two equations, I'm going to substitute this value that I have for x here. So this is what I'll have. I'll have 3 times x minus 2y plus 4z is equal to 1, and I'll have negative 6 times x plus 4y minus 8z is equal to negative 2. And let's see, let's plug these in. I'll have the x that I'm plugging in here is actually going to be 1 minus 3y plus 9z. And I'm also plugging x in here, 1 minus 3y plus 9z, because that's the expression we got for x when we solved it in the top equation. So I solved the top equation for x, and I plugged that expression that I got for x in the bottom two equations, giving me a new system of equations. All right, so I have this new system of equations, and notice this new system of equations only has two unknowns, and there are only two equations in the system, but there are only two unknowns, so that's okay. So let's go ahead and simplify these two. Let's distribute the 3 to give me a 3 minus 9y plus 27z, and then minus 2y plus 4z is equal to 1. And I'm going to distribute the negative 6 too, so I'll get negative 6 plus 18y. What's that going to be? That's going to be a minus 54z, and then we have a plus 4y, and a minus 8z, and this is equal to negative 2. So now I'm going to combine the like terms and move the constants to the right side. So the like terms here, let's see, I have negative 9y and a negative 2y, which when I combine them, I will get a negative 11y. Negative 11y. I have here a 27z, and a plus 4z, that when I combine I'll get a plus 31z. And I have here a 3 that when I subtract it from both sides, it disappears from over here. But then I get 1 minus 3 on the left side, which is negative 2. On the right side, I mean, sorry, on the right side, which is negative 2. Down here, I'm going to combine like terms too. I have here a 18y and a plus 4y, which will give me a 22y. 22y. I have a negative 54z and a negative 8z, which is going to be negative 62z. And then when I add my 6 to both sides, this cancels and I get negative 2 plus 6, which is positive 4. So now I get this as my cleaned up system with 2 equations and 2 unknowns. And once again, I am going to use substitution. So I'm going to solve the top equation for y. Solving this top equation for y yields y is equal to 31z plus 2 over 11. 31z plus 2 over 11 if you solve that top equation for y. Now I'm going to plug that into the bottom equation. So I'm going to have 22 times y minus 62z is equal to 4. So I have this, and I'm plugging in the value that I just got for y, which is 31z plus 2 over 11. So I have this now, which is one equation with only one unknown. My unknown is z, and I can use this equation to find z. Well, first of all, 11 has a common factor with 22. 11 goes into itself once and into 22 twice. Then I can distribute this 2, leaving me with 62z plus 4. Then I have this minus 62z, and it's equal to 4. And once again, I have the case where the 62z and the negative 62z cancel, leaving me 4 is equal to 4. And if you wanted to, you could subtract 4 from both sides, giving you 0 is equal to 0. At the end of the day, the point of this is, unlike the last statement, you see the last statement when we went all the way down, the last statement we got 0 equals negative 21. There were no variables, and that was a false statement. So here we have another case where there are no variables left, but the statement that we have here is not false. This is a true statement. So this isn't the case where there's no solution. There are actually infinitely many solutions here, and as a matter of fact, any point on the line is a solution to this system of equations, because it turns out that they have equivalent equations. They have equations that represent the same line. So what we have to do is we have to choose an arbitrary variable. We have to choose a variable to make arbitrary. We can either make x, y, or z arbitrary. But looking at what we've been doing here, the last equation we had only had z in it. So I'm going to go ahead and I'm going to let z be the arbitrary value. Let's call it a. So I'm calling z the arbitrary value a. That's just a value of z. Now, if I choose this particular value of z, the only thing I have to make sure is that the other two values, x and y, come from an ordered triplet that's also on the line. So all I have to do is make sure I find equations that are true for y and x and plug in the value that I have for z. For instance, here's an equation for y that is true, and it only involves z, which I just fixed as the letter a, or the number a, the constant. So I know y is equal to 31 times z plus 2 over 11, and I fixed z as the number a, so that tells me that y is equal to 31 times a plus 2 over 11. So now I have a value for y based on my value that I chose for z. And now all I need is a value for x. So let's go all the way back up. I know something about x. Let's see, all the way up here. I had this expression up here that said x was equal to all of this. And all I have to do is plug that all in. And I will have my expression that I can use for x in terms of a. All right, so I have x is equal to, and it's going to be 1 minus 3 times, and what I have here is y. But y, remember, was 31a plus 2 over 11. And then this is going to be plus 9 times z, but remember that z was just a. So now I have an expression that can give me x in terms of a. And it turns out when you simplify all that, you get that x is equal to 6a plus 5 over 11. So there I have all my values. I have my ordered triplet. It's going to be 6a plus 5 over 11 for the x value. The y value is going to be 31a plus 2 over 11. 31a plus 2 over 11. And the value of z, we just fix z as the letter a or the number a. So this would be the solution set. It's not just one ordered triplet. If you give a value for a, I can value, or sorry, if you give a value for z, let's say the value a, I can find the value of x and y with these two expressions. So any point that conforms to this ordered triplet is a solution, and there are indeed infinitely many solutions to this system of linear equations.